Physics students, good afternoon. Mr. Fugit here. Today in our video, we're going to be looking at solving through group problem number 5, which specifically relates to our unit 5 on uniform circular motion. Here in our video, as I mentioned, we are going to be looking at group problem number 5. So as a reminder, copies of the group problem, as well as a key for the problem itself, are located on Canvas. I won't have the group problem up on the screen so that we have a little bit more space to work. So if you do need a copy of the problem itself, you're welcome to access that through Canvas or to pick up a hard copy in class. So I'll begin by reading through a part of the problem just to give us a bit of context for what we're going to do. Here in group problem 5A, we're going to look at designing a circular or cylindrical shaped ride for an upcoming theme park. As the ride begins, the riders will stand around the edge of the ride. The ride will start to spin in a circle, and then the floor will drop out, and the design of the ride is meant to function such that the riders do not slide down. In the group problem, you have a picture that you are given that looks approximately like this, from a bit of a bird's eye view, and you're told that we have riders against the wall. Imagine there are several all around, and then the ride's going to begin to spin around in a circle. So, it gives us a bit of an idea of what's going on. We are given a few mathematical values in the problem statement, which are important for us to pay attention to. We're told the coefficient of static friction between the riders and the wall as they stand against the wall is 0.3. We're told the mass of the riders we can design to be about 60 kilograms. Again, we don't know the mass of every rider. We'll design this just for an average human, probably roughly an adult human. And then we're told the radius of the circular shaped ride itself is 7 meters. At the end of the problem statement, we have a question that looks like this. Your job will be to determine how fast the cylinder will need to spin in order to prevent the rider from sliding and eventually to determine if this speed is safe. So, we want to find how fast the ride needs to go in order to keep the riders from sliding, and 2, if that's a safe speed. So, that being said, we are actually being asked to solve for velocity. Right? The how fast question means we want the term velocity. Okay, there's a lot of information that we're given and a lot of different things that we need to try and work through in order to get to the answer that we're looking for. As you've seen in this class, oftentimes, when we're dealing with forces and motion and the radius of an object and the mass and finding a velocity, there's probably going to be more than one thing we have to do. But we need to start by understanding what we're trying to find and how we're going to get there. What's the one thing this problem asks us to find? Velocity, which means we need an equation where velocity shows up. Now, because we're dealing with an object moving in a circle, then we know there has to be some centripetal force causing our object to move in a circle. Objects moving in circles do not occur unless there is a centripetal force. There must be a force directed toward the center of that circle to keep our object moving in a circle. We have an equation for centripetal force, mv squared over r, where m is the mass of our object, rotating, v is the velocity of the object, and r is the radius of the circle it is moving in. Now, that equation has velocity in it, right? Also has mass, which we know, also has radius, which we know, and has fc. We don't know fc yet, but we might be able to get there eventually. Now, the only other equation we have for velocity for an object moving in a circle is this. The velocity of an object moving in a circle is the circumference, the distance the object would travel from one point all the way around the circle, divided by the period, which is defined as the time necessary to make one complete revolution. Here in the problem, we don't know anything about times, so we probably can't use this approach. Would be nice because it's a very direct equation, but we don't have enough information. So, we probably need to find what is the centripetal force so that we can use the equation in blue. So if we want to know anything about forces, we probably need to go back to some of the things we learned in Unit 4. How to draw a free body diagram and applying Newton's second law. So, the picture that we have right now is kind of a top-down view, which doesn't really help us see all the forces very well. It would be hard to see the direction of the force of gravity and that sort of thing. So we might take a side view here, which can help us see the forces drawn out a little bit better. So let's say we have, let's go with a wall. This is the wall here. And then we've got our rider kind of back against the wall, or you can imagine close to against the wall, like something like this. Right? So the rider's standing, your back's kind of against the wall. So, in drawing our free body diagram, usually the first place we start is with our force of gravity. Gravity is a force of attraction between any two things with mass. Here, that would be the earth pulling on you. So the force of gravity is pulling you toward the earth. So we draw that down, F sub G. And then we're told that there's some friction here because we're preventing the rider from sliding. So as you can imagine, once the floor falls out, so imagine the floor kind of drops down here, we want there to be enough friction such that the rider doesn't slide. So if the floor drops out, the rider would want to slide down. Imagine if the wall was completely smooth, but there's going to be some friction that opposes their motion downward. So we'll draw a force of friction vertically upward. That's a little bit different than how we've normally drawn the forces of friction. Typically we have objects that are on flat ground or even on an incline. But here, because our contact surface is vertical, friction is going to be in line with that contact surface. Now, if there's friction, there's by nature going to be some type of contact. Contact specifically between the wall and the rider. Now, that contact is always going to push the object perpendicular to the contact surface. A normal force, by definition, was always going to be perpendicular to our contact surface. So if our wall is vertical, perpendicular to that wall is going to be straight out at a 90-degree angle. Which means the wall is going to push the rider inward, which is a good clue for whether it's going to be our centripetal force or not. You can also imagine if the wall was not here and the ride began to spin, well, your body's going to resist that. There's no wall to stop you. You're going to fall back. Okay? So now we have our forces laid out on our free body diagram. So the question becomes, which of those three is going to be our centripetal force? Well, if I look at the picture, gravity, is that directed toward the center of the circle? No, it is not. Force of static friction, is that force directed toward the center of the circle? It is also not. The only force directed toward the center is our normal force. Now, we're not going to write the centripetal force on our free body diagram because that can oftentimes be misleading and it can actually prevent us from really seeing exactly what all the forces are doing. But we are going to make a distinction here in that our normal force is going to act as our centripetal force. Remember, centripetal just means toward the center. Any of those forces could be acting as our centripetal force if they're acting toward the center. So, now we have an idea of which force will be Fc, so that we can maybe get our way to finding Fc. So once we know Fc, remember, we know mass, we know radius, we can find the velocity. So, do we have any equations for Fc? Well, if you remember all the way back to what we covered in Unit 4, normal force doesn't have an actual equation. The only way we usually can find normal force is using Newton's second law, or maybe using our equation for the force of friction, because normal force does show up there. So I'm going to write out my equation. F sub s is equal to the coefficient multiplied by the normal force. Now, oftentimes we might see this written as force of static friction is less than or equal to the coefficient of static friction times the normal force. Here, we're going to say that it's equal because we're trying to find the maximum velocity we can be at. So, we actually know the coefficient, Fs, but we don't know the force of static friction. So really, if we can find what this value is, we can find our normal force, which can then help us to find our velocity. Seems pretty straightforward. So, how do we find Fs? Well, that seems like it's going to be a problem, because usually, this is the equation we use to find forces of friction. So, the only other thing we can maybe do is to see, is that force of static friction related to some other force? Look back at your free body diagram. I want you to think carefully for a moment about what that free body diagram is representing. There's a force of gravity wanting to pull your body down. There's a force of static friction resisting that pull, or at least preventing you from sliding down the wall. Now, we're told that we want to design the ride in such a way that the object or the person does not slide down the wall. which probably means that those forces should be close to equal. Because if they're not equal, well, our object's going to move, our rider will move, which we don't want. So, how do we prove that? Well, we can do that using Newton's second law. So, I'm going to write that out. The sum of forces in the y direction is equal to the mass of our object multiplied by its acceleration in the y direction. Now we have two forces here, vertically. Static friction up, so we'll say it's positive. Force of gravity down, which is why we'll say it's negative. So when we sum them up, we're actually subtracting them. Now, that's equal to the mass of our object multiplied by the object's acceleration in that respective direction. But remember, the ride is going to be designed to prevent you from sliding. So if you stay stationary, what is your acceleration? Hopefully we can identify that as 0. And any value times 0 is going to give us the result of 0. So now we'll have an equation that looks like this. Fs minus Fg equals 0. I can then add my force of gravity term to the other side of my equation, and we can now show that our force of static friction is equal to our force of gravity, which is a very important thing for us to do because we have an equation for the force of gravity. We know that value, or we know how to find that value better. So, now that we have our force of static friction as equal to our force of gravity, which again, you might have been able to get to on your own, but it's important that we know why they're equal. Here's what we can do. We know that our force of gravity is equal to, well, the mass of our object multiplied by acceleration due to gravity. So let's plug in what we know. 60 kilograms multiplied by 9.81 meters per second squared. Plug that in real quick. Gives us right about 588.6 newtons. So now we have a value for our force of gravity. And so, once we have that, we actually also know our force of static friction. They must be equal because of Newton's second law. No acceleration, our forces have to be balanced. So now we have our force of static friction, which again, isn't our answer, right? At least our final answer, but it's going to help us get there. So I can come all the way back up here, plug into my equation with the normal force, the coefficient, and the force of static friction to get to our normal force, right? And then once we find our normal force, we can come back up here to find our velocity because our normal force is equal to our centripetal force. So there are a lot of steps that we're going through, but we have to keep asking ourselves, what equations do we have? Do we have enough information to solve those equations? We started here with the centripetal force. We identified that as equal to our normal force, and then we worked from there. Normal force shows up in this red equation here. We need to define the force of static friction, so we use Newton's second law to get ourselves there. So, I'm going to come to a new page here so we have a little bit more space. I now know the force of static friction, so I'm going to plug into this equation here. Force of static friction is equal to our coefficient multiplied by the normal force. So here, 588.6 newtons is equal to our coefficient, 0.3, multiplied by the normal force, Fn. So, pretty straightforward now, we can solve for the normal force. So we'll divide by our coefficient, 0.3, on both sides of our equation. 0.3 over 0.3, those values will cancel out to 1. We'll have 588.6 divided by 0.3. That gives us a value of 1,962. So now we know our normal force, Fn, is equal to 1,962 newtons, which is very helpful because our normal force is acting as our centripetal force. So we can set that equation equal to this value. So here we go. Now that we have our normal force, we can move on to show that our normal force equals our centripetal force. So the normal force is equal to this equation, mv squared over r. Now something we need to understand is this. The normal force is acting as our centripetal force in this scenario. The normal force will not always be the centripetal force. It depends on the direction of our forces. The normal force is only our centripetal force here because it's directing our object toward the center. It's pushing our object toward the middle. Okay, so now we know, well, all the values in our equation. Normal force was 1,962 newtons. Our mass, 60 kilograms. Our velocity, well, we don't know, so v squared over the radius, 7 meters. Okay, so we have all of our variables, we've put them into the right places. Now we need to get the velocity term by itself. So let's start by getting rid of what's in the denominator. So we'll multiply by 7 meters up to the numerator on both sides of our equation. So 7 over 7, those will cancel out. So I'm just going to go ahead and erase them. Hopefully that doesn't confuse us too much. And if it did, just rewind the video and watch again. And we just multiply the 7 up. And then we can divide by 60 kilograms. So 60 over 60, those cancel out. I also have to divide by 60 on the left side of my equation, because again, the sides are equal, so we have to keep them balanced. So 60 over 60, those will cancel out. And now we'll have an equation. Oh, no. This that won't work. I'll just move this over. V squared. So, what I'll do here, to make this a little bit easier, I'll go ahead and multiply the left side of my equation, the numerator, divide by the denominator, so we can turn them into just one number. So 7 times 1962 divided by 60 gives us 228.9. But remember, that's still equal to v squared. So the last thing we'll need to do here, hopefully you can see, is take a square root. So the square root of v squared will just be v, and that will equal 15.13 meters per second. So, now we have an answer to our question. How fast must the rider be moving in order to prevent the rider from sliding down the wall? Now, the second part of our question was to determine if this speed is safe. Well, how do we know? 15.13 meters per second. About 30-ish miles an hour, a little more than that. Might seem fast, might seem slow, who knows? But the speed alone, or the velocity better yet, doesn't really tell us if it's safe or not. But what we can determine, based on the velocity and the radius, is going to be the g-force on the riders. And that's going to help us determine if the ride is safe. Hey, because the human body has specific limitations on what are probably good or not good for it. And we want to make sure we're not exceeding those limitations such that it will endanger the riders. So we have an equation for g-force that looks about like this. Not about, looks exactly like this. Our equation, g-force, g sub 0, is equal to our centripetal acceleration divided by acceleration due to gravity. Remember, the g sub 0 is g-force. Little g by itself is acceleration due to gravity. So we need to find our our centripetal acceleration first, which now we can do that based on the velocity. So centripetal acceleration is equal to v squared over r. Our velocity we determined to be 15.13 meters per second. We will need to square that value, divided by the radius, 7 meters. Plug this in real quick. We get right at 32.7 meters per second squared. So now that we have our centripetal acceleration, not too bad to find, we can plug into our equation for g-force. So our centripetal acceleration, 32.7 meters per second, divided by acceleration due to gravity for the Earth, 9.81 meters per second. Move this over a little bit so we have some more space. There we go. We'll plug this in. And we get approximately 3.33. This is the value of g-force, which, as we talked about, isn't a real force. It's a measurement of really the ratio of our accelerations. So this means we experience 3.33 g's of force. Or better yet, 3.33 times acceleration due to gravity. Now, is that safe or not? Well, it seems pretty low based on what we maybe have talked about in class about the limitations of g-force. But the problem statement also tells us that we'll assume that 6 g's is the limit of what is considered safe versus unsafe. And here we are noticeably under the limit of 6 g's. So we can go ahead and say, yes, this is a safe ride. So, hopefully this gets us going on how to set up and solve a more complex problem involving uniform circular motion. Again, remember, we're still using some concepts from what we've already learned in Unit 4. Those concepts are not going to go away. We're going to keep using them continually. Okay? How to draw a free body diagram and analyze forces, how to use Newton's second law to show the relationship between forces, and then using a lot of our equations for forces in order to look at the motion of an object and what causes our object to do the things it's doing. As a reminder, there's also a key for the problem on Canvas. Hopefully this gets you moving in the right direction.